Hello everyone, and welcome to this video on section 6.3 slash 6.4, where I'm just going to be going over one particular objective heading in a Newton Alta assignment for section 6.3 and 6.4. And in this video, that objective heading is called Binomial Series. So in this video, we'll be going through just questions related to the objective binomial series in a preview version of a Newton Alta assignment. Please understand that the questions I see in this video may not be the same exact questions you see when you work on the assignment yourself, but I'm hoping that the problems are similar enough, and watching me do them, will help you out some way when you work on the assignment on your own. All right. So here's what the Newton Alta assignment page looks like. Upper left corner, you have the title of the section without the word preview. In the upper right corner, you have your mastery bar that tells you how far along you've gotten. Now, I'm not going to be completing the entire assignment today, right? If I look at the activity log here, there are objectives with big bold headings and sub-objectives. I am going over the objective with this heading today, the binomial series. And the only objective in this is use a binomial series. Okay. And I'll have one more, and I've already made videos for Taylor and Maclaurin series and Taylor's theorem with remainder. So if you want to take a look at those on my page, you can. And after this, I'll be making another video later on the functions expressed as Taylor series objective. But for right now, binomial series. All right, then on your main page, you have the current objective. Beneath that, a question related to the current objective. Now, at the bottom of every question, you should be seeing a feedback button. All right, if you see any problems with the question itself or with the answer explanations, you can send feedback directly to Newton support, and hopefully someone will get back to you in a reasonable amount of time and help you fix the issue. Next to that, you will not have this instructor cheat button, right? This is just for me, for instructors only. But you should have a more instruction button. All right, so if you're struggling with a topic or a particular question, click on this and you'll be taken to a page with more reading to do or videos to watch or both. And then you'll be given questions to work on that you can do while referring to the instruction. The instruction will still be up. And you can work through the entire assignment with this more instruction each and every time. All right. So as I said, the only objective we're working on here in this video is use a binomial series. All right, so before I get to this question here, I am going to explain, the binomial series. Okay, so we're talking about a binomial expression raised to a power, to a real number power. Sorry, just readjusting here. Now, Typically, this is introduced in the following fashion. 1 plus x. There's a binomial, right? 1 plus x, two terms, right? A binomial. Raised to a real number power r. So again, r is just some real number. And then suppose I call this, f of x. And then we want to find a, Taylor series, which we've talked about on previous videos for this section 6.3.6.4 assignment. So find a Taylor series, say, centered at, x equals a. And remember what that looks like, right? That's the sum representing this function as the sum from n equals 0 to infinity. And remember the coefficients for this Taylor series. The value of the nth derivative at x equals a divided by n factorial. And then these coefficients were multiplied by powers of x minus a, right? So times x minus a to the nth. So I'm going to start going through here. Let's look at this series here in general. All right, 1 plus x to the r. And I'm going to start taking derivatives and we'll evaluate them at a and hopefully see some sort of pattern here. All right. So there's the 0th derivative. And then for every single derivative, I'm just going to be applying the power rule, right? And then, chain rule would have me multiply by 1 if I'm differentiating with respect to x. So just doing the power rule over and over again. So first derivative would be r times, 1 plus x to the r minus 1. Then the second derivative would be r times r minus 1 times 1 plus x to the r minus 2. Third derivative, and I'll just do I'll go to the fourth derivative here before I write up in general what's happening. I have r times r minus 1, and then times r minus 2 times 1 plus x to the r minus 3, and then I'm just going to do one more derivative here. So the fourth derivative, and like I said, after this fourth derivative, hopefully I can explain to you, the general, nth derivative, what that looks like. So this is r times r minus 1 times r minus 2, and then applying the power rule here, I'd have, times r minus 3 times 1 plus x to the r minus 4 power. All right, so look at what happens here. So here's the, say, 0th derivative, that's the original function. All right. Notice how there are no factors in front of this power of 1 plus x, right? There are 0 factors in front of the power of 1 plus x. And then this power on 1 plus x is r minus 0. And again, I guess technically I could call this thing in front here, 1. Right. Anyway, there's no factors involving r, right, in front of the 1 plus x to the r minus 0. Right? Then the first derivative has one factor involving r in front of the power of 1 plus x, and the power on 1 plus x is r minus 1, and your first derivative, r minus 1. Then the second derivative has these two factors involving r, and it starts with r, and then they just decrease by 1, and you'll see that they keep decreasing by 1 each time. But I've got, two factors involving r in this second derivative in front of the power of 1 plus x, and then the power on 1 plus x is r minus 2, second derivative 2. Third derivative has these three factors, so again, starting with r and decreasing by 1 until there are three factors, and then the power of 1 plus x is raised to the r minus 3. And then fourth derivative has four factors involving r, starting with r and decreasing by 1 each time, r minus 1, r minus 2, r minus 3. And then the power on 1 plus x is this r minus 4. So hopefully the way I've described that, you can see the general derivative, right? The nth derivative here will be, r times r minus 1. Now notice when you have r minus 1, that's the second factor. So the factor number I'm at is 1 greater than the number I'm subtracting from r. And I'm doing this until there are n factors. So times, 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 all the way down to r minus. And then if I want this to be the nth factor, we're going to be subtracting n minus 1. Right? So notice the quantity n minus 1 there. So again, this is n factors involving r times, and then you have this power of 1 plus x, and the power on 1 plus x should be r minus n. And eventually I'll plug in, well, what I'm going to do now is, we plug in a, right? We're trying to find the coefficients of this Taylor polynomial, center to a. I plug in a, and then divide by n factorial. Right, so I'll call these the Taylor coefficients, right? So our Taylor coefficients will look like the following. So again, the nth derivative of f at x equals a divided by n factorial will be this, right? So again, it's r times r minus 1 times r minus 2, r minus 3, r minus 4, all the way down to r minus the quantity n minus 1. Now, if you want to distribute the negative here, that's the same as r minus n plus 1. This is getting divided by, n factorial. And then we have times, 1 plus a to the r minus n power. Right? So this is what all the coefficients look like. Now, this is a lot to write right here. That's the reason I got this expression first. This expression right here is a lot to write. And it's, indefinite. It's incomplete. All right, you got the dot, dot, dot here. So you're going to see some new notation to represent this expression. All right. So this r times r minus 1 times r minus 2, all the way down, r minus, the quantity n minus 1 divided by n factorial, all right, again, this expression I've got in the box here, they're going to write this notation to represent that whole expression. So a big set of parentheses, and then r on top, n on bottom. Don't put a fraction bar. This is not r divided by n. All right, this is not r divided by n. Don't put the fraction bar. And then this is sometimes said as r choose n. Now the reason the word choose is used here very often is because this symbolism, this kind of an expression comes up a lot in what's called combinatorics, or counting problems. We're not going to be doing counting here so much, all right? So just know that when you see the big set of parentheses here with a number over n, so again, the number up here is some real number, and n should be a whole number. All right, so again, r is some real number, and n should be a whole number. All right, so 0, 1, 2, dot, dot, dot. Okay. So just one quick example. If I saw this big set of parentheses with, say, 1/2 in the top part, and I don't know, just 2 in the bottom part. Again, this represents this. So you got a fraction here. So in the numerator, you have a product starting with r. So starting with 1/2, and then there should be 2 factors, right? Whatever the whole number is, that's how many factors involving this r will be up top. And you start with r and you keep subtracting 1. So I got half, and then a half minus 1. Now a half minus 1 is negative half, and there's the 2 factors. And then the denominator of this expression is, n factorial, so divided by 2 factorial. So this would be negative 1/4 divided by 2. That would be considered, negative 1/8. So this 1/2 choose 2 is negative 1/8. All right. So that's just one quick example. And then going back to our powers of, our derivatives of this function, looking at the coefficients, right? This here, right, this r choose n expression is the coefficient on the power of 1 plus x, or 1 plus a. So remember, my initial coefficient was 1 on the 0th derivative. So when n is 0, all right, I'll write that one more thing up. When n is 0, so if you have r choose 0, this is always going to be 1. Okay, I'm going to leave again, that initial coefficient I had in front of 1 plus x. That's r choose 0, and then here's r choose 1. Here's r choose 2. Or sorry, we would divide by 0 factorial, divided by 1 factorial, divided by 2 factorial, divided by 3 factorial to get the choosing numbers. Yeah, so just here's one property of this that you should remember. R choose 0, right? If n is 0, that's 1. Okay. So now that I got all this, we can write up our Taylor series for 1 plus x to the r centered at a. So, and then we'll finally get back to our problem, right? So the Taylor series again. So, 1 plus x to the r, right, should be equal to, and then of course, before I get to the problem, I need to also talk about, interval and radius of convergence and whatnot. Right, this would be the sum n equals 0 to infinity. And remember that value of the nth derivative at a divided by n factorial was this r choose n thing I talked about in the previous page times 1 plus a to the r minus n power, right? Remember, this is on the previous page, right? The way the nth Taylor coefficient looked. And then times, x minus a, your powers of x minus a. Now, if I were to consider this expression here as a sub n, with a sequence of terms we're adding up, then I would also like to, determine our interval of convergence, radius of convergence. Right? So we're taking the limit. It then goes to infinity of that absolute value of the ratio. Right? Remember, a sub n plus 1 divided by a sub n. So this would be the limit as n goes to infinity. Now, because n is going to infinity, right, n is changing. Anything that's not n, x, r, a, let's say it's looking the same as that, but it's a different a. Anything that's not n would be considered constant in this expression, right? N is going to infinity. So the limit as n approaches infinity of the absolute value of, r, choose n plus 1 times 1 plus a. Now, if I replace n with the quantity n plus 1 and distribute the negative, that'll be r minus n minus 1, right? Times, and then, x minus a to the n plus 1 power. Right? And then we're dividing this, right? Dividing this by a sub n, right? The previous term, r choose n, times 1 plus a, to the r minus n. And then times, x minus a to the nth. Now, a lot of simplifying is going to go on here. First, I'd like to take a look at, this r choose n plus 1. Remember, this is r times r minus 1 times all the way down to r minus and then 1 less than this, n plus 1, so all the way down to r minus n. And this is divided by n plus 1 factorial. Now, if this is getting divided by r choose n, remember that's the same as multiplying by the reciprocal of this, which would have n factorial in the numerator, and then r times r minus 1 all the way down to, r minus and then n minus 1 in the denominator. So what you're seeing in this r choose n plus 1 divided by r choose n, every factor up here except for r minus n would get canceled away, right? Because r minus the quantity n minus 1 would be right before this, and then n plus 1 factorial is n plus 1, right, times n factorial, so the n factorials cancel. So I'd be left with r minus n over n plus 1. And then these other two things, just, one of the power in the numerator is 1 higher, um, than well, you just do not one higher, but you just do this one's one higher, this one's one lower, but you just do a division, subtract the powers, right? So this will be the limit as n goes to infinity of the absolute value of, and we just saw this r to choose n plus 1 divided by r choose n simplifies quite nicely to, r minus n over n plus 1. And then we have 1 plus a, and then when you subtract these powers, so we just get rid of the r and the n, you get 1 plus a to the negative 1, right? Times, and then just x minus a, right? And like I said, the a and the x and the a, right, are considered constant here. So this x minus a, over 1 plus a, because this is like, 1 over 1 plus a, that can come out, with the absolute value, of course. So this is the absolute value of x minus a over 1 plus a coming out. Then times the limit as n goes to infinity of the absolute value of. Now, r minus n you can think of as, negative n plus r. Remember, r is constant. N is changing. Divided by n plus 1. And this would be approaching, negative 1. Right? If you first degree polynomial of a first degree polynomial. This expression is approaching negative 1. And the absolute value of that means, we're approaching 1. So this limit here is 1. So our limit is, the absolute value of x minus a over 1 plus a. And remember, we need this to be less than 1 for the series to converge. So this is less than 1 when, the following, when, x minus a over 1 plus a is between negative 1 and 1. I multiply everything by 1 plus a, as long as a is not negative 1, by the way, of course, right? Because if a were negative 1, this denominator would be 0. And then also, you'd have 0 to the r, 1 plus negative 1. When you plug in negative 1 for x, 0 to the r would always be 0, so there'd be really nothing interesting to talk about here. So as long as a is not negative 1 here, and then we multiply everything by 1 plus a. Now, 1 plus a could be negative and it would flip things, but I'm just going to keep it the way it is. So it's the opposite. Negative 1 minus a here, less than x minus a. Let's just assume it's positive, and if it's negative, it would just flip things around. It would end up being the same result at the end, less than 1 plus a, and then adding a to everything. Negative 1 less than, oh, actually, no. Oh, yeah, negative 1 less than x, less than 1 plus 2a. And there's your, interval of convergence. Um, but, the center of this should be at a, right? And, you know, so absolute value of x minus a we see is less than the absolute value of 1 plus a, again, as long as a is not negative 1. Sorry about the clutter there. So my interval, my radius of interval of convergence, that radius of convergence, absolute value of 1 plus a, whatever. Okay, I know it's a lot of letters and stuff, but we should be able to determine interval of convergence, radius of convergence using our ratio test. All right. So this is our Taylor series, for a binomial to a power. And then the Maclaurin with this interval of convergence, right? Its radius of convergence. And then more specifically, right, the Maclaurin series. And then finally, we'll go back to the problem. I know it's been half an hour already, but. And then more specifically, the Maclaurin series, right? Remember, this is just let A be 0, right? Center this at 0. So our 1 plus x to the r will be equal to the following sum from n equals 0 to infinity of this, r choose n, and then times 1 plus 0. So 1 to a power is just going to be 1 all the time, so I'm not going to write that. And x minus 0 to the n. So this looks a lot nicer, right, when we let a be 0. And then the interval of convergence, if a is 0, this is just between -1 and 1 plus 0, right? And then the radius of convergence is 1. So just from -1 to 1. And if you were to check the ends, you could show that the series are divergent. All right. Okay. Fix this up. This is nice to know right here, because I could replace x with something and get a series as long as x is between -1 and 1, kind of like we did with geometric series a lot. If I had 1 plus box to the r, that could be the sum from n equals 0 to infinity of r choose n times something in a box to the nth. And, as long as the thing in the box is between -1 and 1. So finally, back to our problem. So we're asked to take this function here. Now they're asking us to use this interesting substitution. I'm gonna hold off on that. I'm gonna see if we can figure out how to find our Taylor series centered at 2 for this function using what we've seen on the previous pages. So we're given this function 1 over 3 plus x to the fourth, to the fourth power. I'm going to write that, as some binomial to a power. So we got f of x equals 1 over 3 plus x to the fourth to the fourth. Now that is 3 plus x to the fourth raised to the -4 power, right? A binomial to a power. I'm trying to think of how to rewrite this so that we involve x minus 2, right? They want the Taylor series centered at, a equals 2. So that would be this, right? Sum equals 0 to infinity of the value of the nth derivative at 2, right, divided by n factorial, and then times our powers of x minus 2. So I'm going to go through and try to figure out a nice pattern for this nth derivative at 2 divided by n factorial here. Now this one, though, will be a little trickier than what I was showing you earlier, because it's not just, 1 plus something. It's 3 plus, and then, it's not just x, it's x to the fourth. So when I do the derivative and apply the chain rule every time, then I also have to multiply by 4x cubed every single time. Right? So watch, right? For the derivative, right, f prime would have to be, -4 times, 3 plus x to the fourth to the -5th, right, applying the power rule, but then, every single time I'm going to be multiplying by this 4x to the third every single time. Man, this is going to get really yucky, because now I would have to do product rule when I do the second derivative. When I do this, all right, I'll just do this one more. Maybe I will go back and use that substitution they recommended. There's probably a reason they're throwing that up there, huh? So sum from, the second derivative here, product of this times this. So I would have to go through and use the product rule. So that's, first times the derivative of the second, which is 4 times 3 times x squared. Right, 4 times 3x squared. 12. I know that's 12x squared, but I'm writing it as 4 times 3 because maybe I'll see something happening here. And so first times the derivative of the second plus, and then the second times the derivative of the first. Now the derivative of this first thing I'm going to write as -4 times -5 times 3 plus x to the fourth, and then I have -6 as the power. And then times 4x cubed, and you had the 4x cubed from earlier, so times 4x cubed squared. Hmm. This isn't pretty. Because there is some common stuff I can factor out. Both of these have this -4 times 3 plus x to the -fifth in common. Or actually, I could do -6, the lower power. And they also have 4x cubed. They have they don't have 4x cubed in common. Okay, so I don't like the way this is going. All right, it would be a lot easier to do the Maclaurin series if I wanted, but yeah, so instead of doing this, right, just because it's going to get really ugly really fast. Let's take a look at that substitution they talked about. So in the problem, they're saying use the following substitution. And they're saying, hey, b plus something, b plus x. And this x could be any expression with a variable to the r is b plus a to the r times the quantity 1 plus, and then x minus a over b plus a to the r, right? And you see on this side here, you know, b and a, I'm assuming, are, a is the center of our Taylor series, right? So I'm assuming a is going to be 2 here, right? They want a equal to 2. And then b, see, b can be some other expression. I want just an x minus 2 here, right? I want x minus 2 here. Okay, so b and a, line a equals the center, and then this r, our function was 3 plus x to the fourth, to the negative fourth, right? It was r is this power here. So a is the center, which we want to be 2. And then r is the power on our binomial, right? Negative 4. So let's just go here. Let's say BA are constants. And yeah, so B is 3. This expression. And I'm going to replace all the x's with x to the fourth. So this will replace this x here. And again, this negative 4 is r, and the center's at 2. So let's rewrite this as 3 plus 2 to the negative 4 power, right? B plus a to the r times the quantity 1 plus, and then again, the x here is x to the fourth. X to the fourth minus a is 2 divided by, and then b plus a, right? 3 plus 2. And all this to the negative 4. Right? So this is 5 to the negative fourth. So that's 1/5, 1 over 5 to the fourth, 5 to the negative fourth, whatever. 5 to the negative 4. And then this is times 1 plus x to the fourth minus 2 over 5 to the negative 4 power. And then I'm thinking they want me to do this. Right? We saw a second ago, right? I had this up here on the previous page, here a couple pages ago. 1 plus bleh, right? 1 plus something to the r can be expressed as a series like this. All right, so I'm going to do that. So this is 1 over 5 to the fourth, which would be 1 over 625, I guess. Right? That's 25 times 25. So 1/625 times, like I said, this 1 plus something to the power can be expressed as the following sum, right? The sum from n equals 0 to infinity of, and then you had r choose n, on the series here, r choose n. Now r is negative 4. So every single coefficient's going to have this negative 4 choose n part, and times whatever's in the x here, whatever's in that space to the nth. So whatever's in this space, that's this x to the fourth minus 2 over 5. All right, that's in the space of x here to the nth. I guess if you simplify some stuff, or maybe I should just keep this as 1 over 5 to the fourth. Because then if I put the 1 over 5 to the fourth inside, you got a 5 to the nth in the denominator. I can write this as the sum n equals 0 to infinity of, -4, choose n, times, and then you have x to the fourth minus 2 to the nth over, 5 to the n minus 4. Or sorry, n plus 4. Plus 4, because the 5 to the nth, and then times 5 to the fourth, 5 to the n plus 4. I think this is what they want you to do. But the problem with this is this series isn't going to be centered at 2. This is not just x minus 2. This is x to the fourth minus 2, which is really centered if you think about having powers of x minus something. That's centered at the fourth root of 2, not 2. So I'm going to put this in, because again, I think that's why they had us use that substitution. I just don't agree. I don't think that this isn't centered at 2. This isn't multiplied by powers of x minus 2. Again, this would really be centered at the fourth root of 2, right? Whatever makes that thing 0. So let me put this stuff in, sorry. All right, so we got in here, right, the -4, choose n. And I think, again, I think they wanted to have eventually x minus 2 here, but I'm putting x to the fourth minus 2 to the nth here. And then we had, 1 over 5 to the n plus 4 as the other stuff, right? So I'm putting that in the front box, right? So the front box is stuff not involving x. And the box in the middle here is for your r, right? -4, the power on the binomial. And this should be, wow. Again, if it's centered at 2, this should be x minus 2, not x to the fourth minus 2, but this is what comes up when the substitution is made. So I'm going to submit it and see what happens. Yeah, so they're taking this. Again, if you read through, see they went through that substitution they told me to make, right? B plus x to the r is equal to this thing, which is true. And you then you have 1 plus something to a power, which you can in your series, right? That Maclaurin series formula I showed you. Hmm. So I'm going to send some feedback actually about this, because once again, this is not powers. This is a series involving powers of x to the fourth minus 2, not x minus 2. So this would actually be centered at the fourth root of 2 and not 2. All right, so I'll do that and come back. All right, I'm back now. Sorry for the brief pause there, but yeah, hopefully that gets addressed. And of course, right, this should be for whenever x to this function will converge, the series will converge to our function whenever x to the fourth minus 2 over 5 is between -1 and 1. Remember that 1 plus x to a power only converged to that series when x was between -1 and 1, right? So this will only converge to our function when x to the fourth minus 2 divided by 5 is between -1 and 1. But that's not being asked for here, right? They just wanted to fill in the series. So now this one. So then I'm asking us here to fill out the first non-zero terms, the first 4 non-zero terms of the binomial series for this function. So once again, I'll just bring back that Maclaurin. All right, we'll just use the Maclaurin series for the binomial to a power, right? 1 plus x to a power. So I'll keep that up. And we'll take a look at our function here. Right. So again, I had this up, 1 plus x to some power, you know, just like, I might as well do this too. Say 1, just say it's 1 plus whatever, 1 plus something to a real number power can be expressed as a power series. The sum from n equals 0 to infinity of this r choose n deal, and then times whatever was in the box here to the nth power. As long as whatever's in that box is between -1 and 1, though. So this actually gives me not just the Maclaurin, but if I had x minus a here, that would give me a series involving x minus a. That would give me some series centered at a. Anyway, so our function here in this example is this. F of x equals 1 over, 1 plus 5 over x to the 4th power, which is the same as 1 plus, 5 over x to the -4th, right? So it's 1 plus something. So the thing in the box here, the expression in my box is this 5 over x. So I should be able to write this as a power series, right? The sum from n equals 0 to infinity of, and then the value of r here is -4 again. So once again, it's -4 choose n for the coefficients, and then times, 5 over x, that's what's in the box here, to the nth power. Now this is going to happen only when, 5 divided by x is between -1 and 1, which implies that, if you look, the only way this is going to happen, 5 divided by x, the only way that's going to be between -1 and 1 is if x is less than -5 or x is greater than 5. Because when x is smaller than -5, you'd get, say -5/6, -5/7, -5/8. Those are bigger than -1. And when x is greater than 5, 5/6, 5/7, 5/8, 5/9, that's less than 1. Right? It's from -5 to 5. It's between -5 and 5 where you're going to have a problem. Right? So our interval of convergence is actually a split interval, right? Less than -5 or greater than 5 is the interval of convergence here. Well, anyway, there's our series for this function. And we're only asked to write out the first 4 non-zero terms. Okay, so f of x could be equal to, and then let's just plug in 0. Right, so again, -4, choose 0 times, and then, this 5 over x to the 0 will be 1, right? Something to the 0 power is 1. So -4, choose 0, plus, and then -4, choose 1, and I went over how to calculate these, right? We'll write what these values are in a second. And then times 5 over x, to the 1st, plus, and then -4, choose 2, times 5 over x squared, and then the fourth term be -4, choose 3, times, and then 5 over x, to the 3rd power. Now remember I said earlier, if this lower value is 0, right, this is 1, right, so 1, and then -4 choose 1 is to start with -4, and then have 1, that's it, then have one factor. divided by 1 factorial. So this is just minus 4, times 5 over x. So that'd be minus 20 over x. I'll type that in a second. Negative 4 choose 2 is take negative 4 and then multiply it by negative 3. That's 2 factors, and then this gets divided by 2 factorial. Times, and then 5 squared is, 25 over x squared. And then there's a plus and plus. And then plus, and then negative 4 choose 3 is, again, start with negative 4 times negative 3. Oh, no, sorry. Sorry. I'm adding one here. Remember, you should be subtracting one. My apologies. So negative 4 times negative 5. Right, remember, you keep subtracting 1 from r minus 1, r minus 2, and so on. So, sorry, that's negative 4 times negative 5 over 2 factorial. Here, it should be negative 4 times negative 5 times negative 6, right? Again, keep decreasing by 1 until you got 3 factors. And then divided by 3 factorial. Right? And then times, 5 cubed is 125 over x cubed. All right, so now I actually simplify this stuff. First term is 1. Then we have minus, 20 over x for the next term. And this is positive 20, but then divided by 2 would be 10 times 25 is 250, so plus 250 over x squared. And then, 3 factorial is 6, so that'd just be negative 1 now. So we have positive 20 times negative 20 times 125, that'd be 250 with a 0, right? So it's 100, but negative, right? Negative. So minus 2500 over x cubed, right? And so on, of course, but this is all they want, right? The first 4 non-zero terms of this series for our function. So we got 1 plus negative 20 over x plus 250 over x squared plus, and then negative 2500 over x cubed. Should be good. Yeah, wonderful. Yeah, so again, you keep subtracting 1 from those factors of r in the numerator there. Okay. All right, so this time we're asked to, again, use this Maclaurin expansion, right, to 1 plus x to the r and write a power series for it, centered at 0. For this function, 1 over 1 plus 3x squared to the 4th, and use this to find a 6th order Maclaurin polynomial. Right, so we go out to the sum from 0 to 6, right, get to the, well, actually, we won't have to go out to 6. You'll see, because there's 3x squared down here. If I want the 6th degree polynomial, I'm not going to have to go that far to get to the 6th power. You'll see that. In order to estimate, we're divide by 7/4 to the 4th. So back on here again, I'm using this. All right, they're giving us this expression again. Right, how to take a binomial to a power and write a series. So this time our function is 1 over 1 plus 3x squared to the 4th power. Again, it's the 4th power. I don't know why they keep throwing the 4th power in this here. Just know that you might come across problems where there's not a fourth power, but this is this binomial 1 plus 3x squared to the negative fourth, right? So this 3x squared is going to replace the x, right? 1 plus something, and then r is negative 4. So this should be the sum from n equals 0 to infinity of, negative, once again, r is negative 4. So negative 4, choose n, and then the thing in the box, right, the thing replacing x is 3x squared, right? So times 3x squared to the nth. Now this is only going to converge to that function when 3x squared, is between negative 1 and 1, which would only happen when x is between negative square root of 1/3 and positive square root of 1/3. So a pretty small interval. Anyway, now they want us to use the sixth order, right? Sixth degree Maclaurin polynomial, right? This would be centered at 0 still. Right, if I had this would be the sum from n equals 0 to infinity of this negative 4, choose n, times 3 to the nth, times and then x to the 2n. So you see how every single term here is going to have an even power, right? X to the 2n. So if I'm going to the sixth order, the sixth degree, I don't need to go out to n equals 6. I just need to go out to n equals 3, right? That would be 2 times 3, that would be the sixth power. So I'm just going to write up the first, until n equals 3. So that'll be the first 4 terms of this. So you'd have negative 4, choose 0. And then times 3 to the 0, x to the 0. So just negative 4, choose 0. So just 1 for the first term. Plus, and then negative 4, choose 1. Times 3 to the first. Times x squared, right? X to the 2. Right? So there's your second Maclaurin polynomial. And then plus, and then negative 4, choose 2. Times 3 squared times x to the fourth. And then finally plus, negative 4, choose 3 times, 3 cubed times x to the sixth. There's, I'll say, and then dot, 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 right? Now, if we just stop it there, right, we're going to say then f of x is approximately, right, now I'm not using equals, this is approximately just out to the sixth here. Now, negative 4, choose 0 is 1. Negative 4, choose 1 would be negative 4 times 3 would be negative 12, so minus 12x squared. Negative 4, choose 2 would be negative 4 times negative 5, right, decreased by 1, and then divided by 2 factorial. So that's 10 times 9, right, 3 squared is 9. So this would be plus 90 x to the fourth. And then negative 4, choose 3, we saw in the last one, that's negative 4 times negative 5 times negative 6. Divided by 3 factorial is 6, which makes this negative 1 here. That's negative 20 times, 27. 3 cubed is 27. So that'd be minus 540, right, x to the sixth. So there's the sixth degree, sixth order, sixth, Maclaurin polynomial we're going to use to approximate our function. Now they're asking us to estimate, using this here. I'll definitely go to a calculator for. They're asking us to estimate and round to 3 decimal places. 1 over 7/4 to the fourth. Well, remember our function was 1 over, 1 plus 3x squared to the fourth. 1 plus 3x squared is going to be 7/4. Well, we have to figure that out, right? 1 plus 3x squared. When's that equal to 7/4? I would subtract 1, get 3x squared. Now that's 4/4, so that'd be 3/4, and so x squared would have to be 1/4 And so x would have to be plus or minus a half. I'll just use a half, right? So this is f of a half. When I plug a half into my function, we're getting this value here. So if I call this, this is P6 of x, right? The 6th-degree Maclaurin polynomial. It should be approximately the value of P6 at a half, right? So I'm going to plug in a half to this, and then they're asking us to, round to 3 decimal places. So I'm going to go to the Desmos calculator again. Well, I haven't done it this video yet, but you've seen me do it plenty in other videos. So say I have f of x equals, I'll put in our function 1 over, 1 plus 3x squared to the 4th. And then here's our polynomial, right? The 6th order polynomial is 1 minus 12x squared plus 90x to the 4th minus 540x to the 6th. And you see that near 0, right? Maclaurin is centered at 0. You see how near 0 the graph of our polynomial is pretty darn close, very, very close to approximating the red curve, right? The graph of our function. But then the further away from 0 we get, of course, it's way off, right? Deviates from it quite a bit. Now here's the actual value of the function at a half, right? When I plug in a half, there's the actual value of 1 divided by 7/4 to the 4th. Now look at our polynomial at a half. And that's actually quite a bit off, right? Because a half is here, so my cursor's floating. Remember I said earlier, the function, the series, right? Remember I said earlier, our series will converge to this function only between these values, negative square root of 1/3 and positive square root of 1/3. Well, these are, a half is not in here. Right? A half is not in here. A half is bigger than the square root of 1/3. Right? It's actually the square root. Oh no, a half is in here. Sorry. But the 6th-degree let's just double check. Square root of 1/3 is definitely bigger than a half. Okay. Yeah, because like 1/4 is smaller. Right? Square root of 1/4 would be between. All right, so it'll be less than. But it's close to the edge though, right? A half is out here. Right? Because here's 1. A half is here where my cursor's floating. So the 6th-degree polynomial isn't great, but if I added more and more terms on, it would get better and better than a half. But they're only asking for the 6th-degree one, so negative 4.813 if I round to 3 decimal places. So negative 4.813. It's not a great approximation, but it's what they want. Okay, again, the higher degree you got, the more and more terms you threw on, the closer it would actually get. Yeah, so we're seeing the 6th-degree one is actually not a great choice. We'd have to go a little bit further for a better, more accurate approximation. All right. So again, another estimating problem. All right, so very similar to the last one. So once again, we're asked to use this statement, right? Remember, this is our binomial series. All right. Call this the binomial series here. And the function we're given is 1 over 1 minus 2x to the, this time it's the 2nd power, not the 4th power. Hooray. Now, if I think of that as 1 plus something to the r, it would be 1 plus, negative 2x to the negative 2. It's 1 plus something. 1 plus something to the r. So whatever's here replaces x here. So this should be equal to this series. Only for certain values of x, though, and we'll talk about that too. Sum from n equals 0 to infinity of, negative 2 choose n times, and then negative 2x to the nth power. Only, this series will only converge to this function value when negative 2x is between negative 1 and 1. Dividing by negative 2, that'll flip everything. And x needs to be between negative half and a half. So when x is between negative half and a half, this infinite series will converge to this function value, this value here. Now they're asking us to use the third order Maclaurin polynomial. So f of x here, I'm going to say is approximately, and then we're just going to have to go out to n equals 3. Right. So when n equals 0, you're going to get, negative 2 choose 0 times something to the 0, which is 1, plus, and then negative 2, I'll write it out, negative 2 choose 1 times negative 2x, to the first, plus, and then negative 2 choose 2 times negative 2x squared, and then they want to go out to the third, will give me x to the third eventually. So negative 2 choose 3 times negative 2x to the third. Right? So this is 1. Now negative 2 choose 1 is just negative 2, and then negative 2x to the first is negative 2x. That'll be plus 4x. This would be negative 2 times negative 3 divided by 2. So it's, just 3. 3, and then times 4x squared, so plus 12x squared. And then this, negative 2 choose 3 is negative 2 times negative 3 times negative 4 divided by 6, but that cancels these. So that's just negative 4. And the negative 2 cubed is negative 8. So positive 32x cubed, right? So here's P3, right? This is the third degree polynomial that approximates our function. And we're asked to estimate 1 divided by 1/3 squared. This is going to be 1/3 when x is negative 1/3. No, when x is 1/3. Sorry. Right, when x is 1/3, you'd get 1 minus 2/3, which is 1/3. Right, so this is just our function when, x is 1/3. Right, when x is 1/3, again, you get 1 minus 2/3, which is 1/3 squared down here. Right. So this should be approximately equal to, the value of this third degree polynomial at 1/3. And 1/3 is in our interval, so we could use this as an approximation, but and the more and more terms that added on, it would actually converge to f at 1/3, but we're using this just to approximate. Now the approximation might not be great, but that's all they want us to do. So I'm going to put this into my calculator again. All right, let's back up here. I'm just going to put the polynomial in this time. Actually, let me put in the function too. So f of x, we were given was 1 over, the quantity 1 minus 2x squared. Right, and we're going to see this polynomial we write up is going to be very close to this function at 0 here, right? These are all having powers of x, so it's centered at 0. So p of x, right, the polynomial, 1 plus 4x. See how this tangent there at the point 0, 1. Then plus 12x squared. So now it's still pretty good. Again, it's only going to be between negative half and a half that the function converges to that the polynomial converges to the function plus 32x to the third. Yeah, so see near, now at a half though, or sorry, a third would be about here. It might be pretty good. Might be pretty good, but it'll be off. But so f of a third, right? The actual value is 9. Right? That'd be 9. And then the polynomial at 1/3 is not great actually at all. All right, but still, this is what they want us to use. Now, the more and more terms that you added on, if I kept adding more and more and more terms of that polynomial, you'd get a closer and closer approximation. It should converge to 9. Right, at x equals 1/3. But 4.852, if I'm running to 3 decimal places, the approximation is 4.852. And not a great approximation, but it would get better and better if I used higher and higher degree polynomials. Good. So now we're back to one of those where they have us use this substitution to get a series centered at 0. So a is 0 here, equals 0. So that'll make this actually a little nicer. We'll actually get a polynomial centered at 0 with this substitution instead of like in the earlier problem. So back to my paper. So again, keeping this in mind, this is going to still come in handy here. F of x is the square root of 4 plus x squared, which you can think of as, 4 plus x squared to the 1/2 power. So when they're talking about this substitution, b plus x to the r, b is 4. They said they wanted it to be centered at 0, so a is 0, and then r is the 1/2. So we're making this substitution here, b plus a to the r times, and then 1 plus, x minus a over b plus a all to the r. And then here's where we're going to use our series statement, right? 1 plus something to the r, I can write as a series. So making all these substitutions, 4 for b, 0 for a 1/2 for r. We just have, 4 plus 0, this 4 to the r right here, 4 to the half, square root of 4, times, well, that's just 2. I can write that as 2 in a second. 1 plus, and then x minus a, that's just x over, and then b plus a is 4 plus 0, that's x over 4, to the half. So this is 2. This here I can write as a series, this way where x over 4 is replacing the x and half is replacing the r. So the sum from n equals 0 to infinity of 1/2, choose n, times, and then x over 4 to the nth, which is going to be centered at 0 properly. Not like that earlier problem. It wasn't centered at 2. And then if I put the 2 in, 4 to the n is 2 to the 2n. So I'd have 2 to the 2n in the denominator. And this is 2 to the first, so I have 2 to the 1 minus 2n power, right, to dividing things to subtract, times half to the n, half choose n, and then times x to the nth, and this is what they want right here, right? Fill that stuff in. Now, of course, this would only converge to this when x over 4 is between -1 and 1, right? So when x is between, this would be for when x is between -4 and 4, right? This series would converge to our function, this square root, but they just want us to fill this stuff in. So out in front here, 2 raised to the 1 minus 2n power. Then you have times the half, choose n, put a half in that box, and then just times x to the nth. So it's centered at 0. And that should be good. What did I mess up? Okay, let me just double check here. B was 4. R was a half, right? Square root. Oh, the function's 4 plus x squared. I'm sorry. It's 4 plus x squared. So x squared replaces the x. So this should be x squared. So this should be x squared. And then this is x to the 2n. That's all. So let me put x to the x squared in that box, right? This should be x squared to the n in that box there. All right, so good. They give me another shot here. Wonderful. All right, my apologies. I messed up then that little 2. All right. All right, and then one more here. Looks like, well, I'm hoping be close to being done with this objective. Got another series here that I can write and write as a binomial to a power, 1 plus something to a power, and then rewrite it using this rule here, right? Our binomial series rule. Right, so our function is 1 over 1 minus 1 over x cubed, which I can think of as 1 plus negative 1 over x to the negative third. Right, so x is being replaced by negative 1 over x, and r is being replaced by negative 3. Right, so this should be the sum from n equals 0 to infinity of, negative 3 choose n times, and then negative 1 over x to the nth power. When negative 1 over x between negative 1 and 1. So this is only going to happen here if x is less than negative 1, right? Because that would give me the negative 1. Negative 1 over negative 2 would be a half, and then 4 is worth a fifth, and blah, 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 right? Or when x is greater than 1. Right? When x is greater than 1, you'd have negative 1 over 2, negative 1 over 3, negative 1 over 4. Those would be greater than, between those two. So interval of convergence there is another split one. Now we're only asked to write the first 4 non-zero terms. So you got negative 3 choose 0, which is 1, plus, and then negative 3 choose 1 would be negative 3, and then times, negative 1 over x to the first, plus, and then negative 3 choose 2, that'd be negative 3 times negative 4, so 12 over 2, that'd be 6. Negative 3 choose 2 times negative 1 over x squared, and then the fourth term, negative 3 choose 3, would be negative 3 times negative 4 times negative 5. So that'd be negative 60 divided by 3 factorial divided by 6 would be negative 10. So minus 10 here times negative 1 over x to the third. And so first term is 1, second term is plus 3 over x, then plus 6 over x squared. And then negative 1 cubed is negative, so plus 10 over x cubed, right, and so on. But this is all they want, right? These first 4 non-zero terms. So 1 plus 3 over x plus 6 over x squared. The last term here plus 10 over x cubed. Great. All right, so that objective's done. And as I said at the top of the video, all right, this is the only objective I'm doing. this binomial series one. You'll see a video for functions expressed as Taylor series later. You can go back and look at previous ones as well. But yeah, that's it for me in this video. So I hope you know, hope it helps. Like I said at the top, the questions you see here may not be exactly the same as the questions you'll see when you work on the assignment yourself. But hopefully they help you out enough. The way I'm doing things, the types of problems are similar enough that they help you when you work on them on your own. And thank you very much for watching.